This video contains the solution for all the parts for the AP Physics C Mechanics 2009 exam number 1. We are given in this problem a mass, an object with a mass of 3 kilograms, and it's moving along an x-axis, so a rectilinear motion just back and forth, in a region where its potential energy is given by the function. Potential energy is equal to 4x squared. U is in joules, x is in meters, so everything is SI units. And we know that when the object is at negative 0.5 meters, velocity is equal to 2 meters per second. That's also given. Looking at this right here, we know that, generally speaking, the derivative of a potential energy function is negative the force. So let's go ahead and find that force function. The derivative of this would be 8x, so negative of that would be negative 8x. And just with a little bit of forward looking toward our part E of this problem, the potential energy is something x squared. Well, that might put you in mind of 1/2 kx squared, and this might put you in mind of Hooke's law. So maybe we're talking about a spring here, and I think this is going to help us a lot when we get to part E. So good for you if you recognize that. Now part A, we want the total energy of the object. Well, since we have, and they actually say that all forces acting on this object are conservative, so mechanical energy is conserved, which means that potential energy plus kinetic energy is equal to constant. It does not change. Or you could also write that as the change in energy is, what's the change in energy? Think about that for a second. 0. It doesn't change, right? It's constant. So if we can figure that out at any particular point, well, since it's constant and it never changes, then that's the same as it is everywhere. So let's see. We know this, and we know this from our potential energy function. So I'm going to use this point, this location. So potential energy at negative 0.5 plus the kinetic energy at negative 0.5. That would be our constant mechanical energy. So let's see if we can figure that out. So 4 times negative 0.5 squared plus 1/2 mass times velocity squared. If there's the mass, that's the velocity. That gives me a total of 7 joules. That's the total energy at any time. Part B, they're asking us to calculate the x-coordinate of any points at which the object has 0 kinetic energy. Well, since the total energy is always 7, 0 kinetic energy means all 7 joules is taken up by the potential energy. So that would happen when the potential energy, or 4x squared, takes up all 7 joules of the mechanical energy. And that happens at positions plus or minus the square root of 7/4 meters. And you can leave your answer like that. You can use your calculator, give them, I think that's about 1.3 meters, whatever you like. Don't forget the plus or minus. They didn't say anything that distances could only be positive. Part C, calculate the magnitude of the momentum of the object. Well, let's see. So we can find velocities that can give us momentum. So at point 6, we have the potential energy at point 6 plus the kinetic energy at point 6 must be equal to 7 joules, right? Because the mechanical energy is always 7 joules. So this is 4 times 0.6 squared plus the kinetic energy at 0.6, which we're going to find in a second, equal to 7. And I believe this is equal to 1.44, so this is 5.56. And kinetic energy is 1/2 mv squared. So kinetic energy at this location is equal to 7 minus, let me just make sure that's right, 7 minus 4 times 0.6 squared, that's 5.56. And I know what the mass is, so let's see, that's 1.5, mass is 3 times 1/2 v squared equals 5.56. So the velocity, 5.56 divided by 1.5, and then I want the square root of that. And that gives me a velocity of 1.9 meters per second. Oh, but that's not what they wanted. They wanted to know momentum. So, since momentum is equal to mass times velocity, that's multiplied by 3, that's the mass, and that gives me about 5.8 kilogram meters per second. That's the momentum. And if you're wondering about significant figures and all that sort of thing, usually anywhere between 2 and 4 is okay on the AP test. Part D, calculate the magnitude of the acceleration. Magnitude, so they just want positive number as it passes that same point. Well, let's see. We know already, I think we calculated earlier, at the very beginning of the problem, we realized that the force, the function of distance, is negative 8x. So if we didn't do that early on, I think we'd be tempted to do it now, because if you're asked for acceleration, you should think force, right? Because since we know the mass, that means acceleration as a function of distance, not as a function of time, but as a function of distance, is equal to negative 8x. Force equals mass times acceleration, so I divide the mass over to the other side. And that means the acceleration at point 6 is, I'm going to ditch the negative sign because they asked for magnitude. So that's 8 times 0.6 divided by 3, 1.6 meters per second squared. Okay, now part E, they want a couple of graphs. They want a graph of position versus time and kinetic energy versus time. And this is really where it pays off a lot to have realized that we're talking about a spring situation here. And they're telling us here that assume that x equals 0 at time 0. And we also know that some short distance later, when x is negative 0.5, the velocity is positive. So I don't know how much that really tells us here. If this is a spring oscillating, if we realize that it starts here, then we've got some kind of sine curve like this. Draw two periods there. Now, it's a little bit tricky here. It might help to think about what the velocity curve would look like before we get to here, because x of t would be equal to some kind of sine graph, right? Sine of t. The exact details of this really don't matter here because they're just asking us to sketch this and not actually put any scaling on the t-axis. So velocity would be some kind of cosine graph, right? We could figure some amplitudes and so on, but we really don't need to do that here. And then kinetic energy as a function of time would be 1/2 mass, which is just 3/2. Again, that doesn't really affect much. The important part here is cosine squared t. So what does that look like? So it might help us to say, well, if you've got a sine graph, what does cosine squared look like at the same time? And if you're not sure, well, you can always graph that. So let's just go ahead and do what did I draw? 2 periods here, so that would be 0 to 2 pi to, well, let's just do the 0 to 2 pi. That should work. So let's take a look at the sine graph and the graph of cosine of x squared on the same graph. Let's make sure we are in radian mode. We are, because we're taking a derivative, so we have to be. And let's set our window from 0 to, well, let's go to 4 pi. That'll give us the whole thing. And our scales, let's see, -1 to 1 for the y scale. So there's my position graph. Oh, I don't know if you can see that. Maybe you can see that. There we go. A little bit better. And then, so this was position. And then the kinetic energy, when you square the velocities here, maxes out. And because we're squaring it, we never have negative values, so it stays always above. Of course, kinetic energy is always positive, so it makes sense. So when this maxes out, this gets to a minimum and then a maximum again. Does it make sense to you, think about this for a second, that, let me just finish sketching, that the maximums of the kinetic energy, in other words max velocity, happens where the position is 0? Well, sure, if the spring oscillating back and forth, then its maximum velocity and therefore maximum kinetic energy will happen when it's at its equilibrium point. So that makes sense.